DNS security issues.
Who works for an unnamed company, doing unnamed things, but you can ask him all about it as he discusses DNS security issues.
Hi, everybody. To give you a little background on what I do, I am a hostmaster / network engineer. I take care of about probably 120 different zones spread geographically across 5 different countries, and I also maintain routing and other basic networking functions. So today's talk is going to be basically about what does security mean for DNS? DNS has been around. A lot of people know about it but don't really pay much attention to it. So what we're going to talk about is the security problems that exist for DNS and what is being done about them. The IETF is working on a lot of things right now to try to make this a much more secure environment. And what you can do now to prevent any real problems. This is going to be for IT specialists, managers, anybody who has to deal with DNS servers. We're going to start with a brief overview of DNS, what the weaknesses are in DNS, what is being posed in the IETF, what you can do now to lock your servers down and prevent problems, and where you can look for other information. DNS is probably one of the most important services that exists on the internet. Without it, the internet really doesn't function. I mean, in reality, it's all there, right? All the servers are up, connectivity exists, packets are going back and forth, but nobody finds anything. I mean, I would be amazed if there's more than a handful of people here who actually use IP addresses to actually connect to anything. So DNS is going to be what makes or breaks the internet. When people talk about complete denial of service attacks on the internet, DNS is a very key one of those things. Without it, nobody goes in. Some of the problems with it are there's no authentication. DNS packets are UDP, and they're really, really basic. There's just nothing in there for any kind of real security that's provided in the packet itself. We've got new things coming out like dynamic updates that are really cool and make administration really easy, but make security a nightmare. And there's problems like DNS spoofing and cache corruption. Weaknesses we're going to speak about in DNS are ID spoofing, cache corruption, zone transfers, and dynamic updates. Start with zone transfers. Zone transfers it's not something people don't really think a lot about. I mean, it's amazing how many servers out there I found that have opened their zone transfers. They're totally wide open. And it's always a good idea to just lock down your zone transfers. What this allows is for anybody out there to gain a list of every single host you have on your network. And it's really information you don't want people to have. This is a DNS packet right here. As you can see, it's really basic. All it has is how many questions it's going to answer, how many answers, the questions in the answer. The important part is the ID. That is where one of the weaknesses we're going to discuss is focused on. First one we're going to talk about is cache corruption. Cache corruption allows people to put false data into your DNS server. The way this has to work is the attacker has to have a DNS server that is authoritative for some domain. And then what it does is it passes extra data with legitimate answer to the DNS server caches, and then it caches the bad data. And let me show you an example. You have two servers here. One's the attacker and one's the target. The attacker is authoritative for the domain badguy.com. So what he does is he makes a request for www.badguy.com and he attempts to resolve it against the target. The target then goes back to the authoritative server and requests that data. Since it's authoritative, it's the one the root is going to point to, the internet is going to point to for that information. And this is where it happens. The attacker then sends back an answer for www.badguy.com with an IP address, no big deal. But then in that same packet, it sends an answer for www.whitehouse.gov, CNAME back to badguy.com, effectively making it so anybody who uses that DNS server cannot reach the White House website, but now goes to the bad guy's website instead. So now they've successfully managed to corrupt this person's cache. So So then there was another method of doing this. After they found a patch for that, they just discovered another method. This has to do with the fact that the DNS packet itself will accept data if it's got a legitimate request in it. It will accept the bad data, and let me show you that too. So the attacker makes a request like before. The request is sent back as before. Everything's pretty much the same. But at this point, the attacker sends back an answer for test.www.badguy.com. Now, the reason why this works is because the DNS server sees that although this is not the name that was requested, it is within the same zone, so it's totally acceptable. It then CNAMEs that to www.whitehouse.gov and then sends another issue for whitehouse.gov CNAME back. And because it all started out with authentic data, it totally accepts it, and once again, the cache is corrupt. And now we'll move on to ID spoofing, which is another method. This doesn't even need an authoritative name server. This is done, anybody can do this from their ADSL line. Most implementations of bind use a very predictable ID number. You start the bind service, it starts with 1. It sends a query out, it gets 2. You go, next one is 3. I mean, there is no question at all. Each packet is just one increment. So what they do is they wait for they send a request to resolve it. And at that point, they start flooding the server with bad information, with incrementing the sequence number every time. If they find the one in the right sequence number, it accepts the data. This number is only 16 bits, and it takes 65,000 packets to actually, if you tried the entire key set, which you don't even have to do. It can be done with far less than that. At one time, this was not very feasible, but now with people having DSL lines for $60 a pop, you could imagine this could happen a lot. There are actually programs out there that do this. One that I can think of is called .c, which does this very specific thing. Oh, and is publicly available. Right now, the IETF is working on methods of trying to create authentication. Now, as everybody knows, pretty much anything that they're trying to secure now is done through encryption, through authentication. So I'm not really going to go into the different kinds of encryption authentication because that's been addressed over and abundantly, I'm sure, many, many times. So we'll talk specifically about how encryption is applied to the DNS packets itself and what it can do to help your problems. First thing to realize is that what we're going to discuss here is digital signatures, new record types that are created for DNS specifically for authentication, the chain of trust, verify authentication, authenticated denial, and TSIG. Now, the DNSSEC spec does have standards for public key infrastructure, which is something we're not going to talk about, but it does exist. There are 3 new record types that we're going to discuss at this time that the new standards have implemented. They're SIG, key, and NXT. Key records are stored, is the key for the entire zone. So it's built from the parent zone, and it creates a key. This can be either private key or public key. It doesn't really matter, and I'm sure somebody else has discussed which one's better, so I'm not really going to get into that. But the key to remember here is that we're not actually encrypting anything. It's actually the signature part that's important. All we're doing is signing the data to authenticate it. SIG is a signature for each record set. So every record that's asked for has a SIG record associated with it. A SIG is built off the key. The question is, how do you know a key can be trusted? So you're on the internet, your server accesses another server and it requests the data. It returns a key and it says, your DNS server looks at it, but how does it know that this is a valid return? I mean, it could be anybody returning any key. That's where the chain of trust comes in. The SIG record associated with the key is set by the parent domain. So the SOA has a specific key, or SIG, which is set by the key in the parent domain before it. At that point, what you do is it will try to query the information from the parent. If the server already trusts the parent, it will go ahead and accept whatever data is below it. And if not, it will go up the next step. So if we're talking foo.com and it's asked for www.foo.com, It'll look the SIG for foo.com, and if it trusts it, it'll go on. But if not, it'll ask for the key for sig.com, and if it trusts that, and it'll go all the way up to the root, and where the root will have the authoritative CAs and all that other stuff for the infrastructure. This is very helpful to verify authentication. This will stop some of those cache corruption problems I was talking about. If somebody passes a record back for foo.com and also a record for lax.com, it'll say this key is not valid for this domain, hence I will not accept this data and will not cache it. One of the problems with this is it's going to be slow, because anytime you add more lookups into a DNS lookup, it slows it down. And as some of you probably know, DNS servers have to go pretty darn fast. Mail servers, especially if you're spammers, just pound DNS servers. But as any other DNS request, once it gets cached, it's cached. No big deal. When they were designing the spec, one of the important things that came out was the problem of authenticated denial. What they found, this was a denial of service attack problem. What they would find is that what you could do is if you were able to grab a signed SOA, you were then able to use that signed SOA later on in other transactions. And let me show you how. This is what's called a replay attack, and this is an example of one. You have a DNS server, we'll call DNS1, asks for test.foo.com. DNS2, which is authoritative for foo.com, but does not have a test record in that, will reply with what's known as an NX domain, which means non-existent domain, and a signed SOA. Basically, all the information it can come up with. DNS3, who's sitting in the middle of all this, captures this information. DNS1 at that point asks for www.foo.com. DNS3 throws the SOA, the signed SOA in the next domain at DNS1, who then says, oh, it's another domain that doesn't exist. So they've now denied service to your web server. We came up with the NXT record, stands for non-existent. The way the NXT record works is when you make a query, let's see. When you make a query for, say, you want an MX record for www.foo.com, what it does is, if that MX record doesn't exist, it will reply back with the NXT record, and it will also reply with any record that exists for that. So it will reply with A records or C names or whatever exists. It says, I don't have this specific one, but I have these. Will these work? The other thing it will do is if no record exists at all, it will actually hand back the record before it and the record after it. Specifically based off of a canonical list that's defined in the standard itself. So, say DNS asks for x.foo.com, and it doesn't exist. So DNS2 will respond with the NXT, plus it will respond with d.foo.com and y.foo.com. And it says, so basically, I have these two, but nothing in between it. And then it says, well, since there's nothing in between it, it doesn't exist. So, let's see if So basically what it does, what will happen is, if the exact same type of replay attack exists, somebody says, I'd like, x.foo.com. And it rejects it, sends an XT in the signed SOA. But what it sends is d and y.foo.com. At that point, so the other person who had captured that same packet then tries to send it back when somebody asks for like l.foo.com, or I should say a.foo.com. It will then, he'll look at it and it will determine it doesn't fall within the actual records that were already specified. So it says, well, since this doesn't fall between F and Y, it's not really valid, so it'll reject it. Okay. Another issue with DNSSEC is what's called TSIG. One of the issues is most people's machines, most resolvers exist on your machine. Your Windows 95 box, your Linux box, your Solaris box, whatever you're using has some kind of resolver on it. As a general rule, these don't cache data. What it does is you point to very specific DNS servers that exist, and you request your resolution from them. So without the caching mechanism, if that resolver can't authenticate it, it'll ask for authentication over and over again. So to eliminate this, they came up with TSIG. What it stands for is transaction signature. Basically what you're doing is you're authenticating the data that goes between a resolver and a known DNS server. So all requests, so what happens is the DNS server starts up, and you decide which server is your DNS server. You configure it in your configuration. It then will create the public or a key set, be it public or private or whatever. It'll create a key, and then each of these, the resolver and your machine will keep that key. And from now on, all transactions will be signed with these keys. One will be a resolution key or resolution signature, and one will be a transaction signature. This signature is not stored in the DNS data, as that could be another form of compromise. It's actually stored they call it out of band, which is not in the DNS data. This is going to be really important, and this is kind of a segue with dynamic updates. I don't know how many people here are really working with dynamic updates, but dynamic updates are really cool. Basically what they allow you to do is you can have your machines pull itself out of DNS or add itself back in. Some people here work with WINS. It's basically the same kind of concept. So you don't have to manually change the DNS entry anytime a machine changes an IP or changes a name. At that point, but this leaves a big security weakness, right? Because if a host can go in and change the DNS entry, that means anybody really can. Having the TSIG means that it will you set it up so it will only accept changes with that private key or with that key. So it helps that. Unfortunately, right now there's not a lot going on. I mean, I was out looking at this, and TIS had made a version of Bind that supported the DNSSEC. Right now, DNSSEC is a moving target, so anything you see out there changes like that. So I couldn't even find the DNSSEC version of Bind anymore, but it's going to be available, I would imagine, probably about a year or two, and then, of course, however long it takes to implement it, which doesn't do a lot of good right now. It's good to stay on top of this stuff and to maybe even pull down some copies, start some testing, but right now, there's big problems on the internet with this, and they're easily accessible. So the question is, what do you do right now to try to patch these holes? One of the most important things is to upgrade your boxes. Most of these, anytime a security hole comes out or some kind of problem comes out, there's an upgrade for it. And it's amazing how many servers out there are never upgraded. For instance, some of the cache corruption ones are fixed in Bind 8.1.2 and 4.9.6, and also in the Microsoft DNS. So whatever version you're running, you should be upgrading, just being on top of it completely, any hotfix. And that includes when you rebuild the machines. One of the biggest problems I find with people with servers out there is they may apply the hotfixes and the patches. Then for some reason their machine blows chunks. So they decide they got to rebuild it from scratch. So they rebuild their machine from their install disks, and then they're done. They don't install hotfixes or patches or anything like that. And once again, they just introduced holes back into their whatever server. And that applies to anything really, but specifically DNS. Restricting zone transfers is a good idea, as I mentioned before. Zone transfers are considered a minimal risk, but they are a risk. It's information that attackers out there, they don't need to know. They don't need to know all your hosts on your network. They don't need to know your IP ranges. They don't need to know any of that information. So it's just better just to lock it down to very specific servers that you want to allow zone transfers. Dynamic updates. If you're using dynamic updates right now, it's you should just definitely lock it down. The only thing that I know of that's doing dynamic updates is Bind 8.1, and it has very good methods of restricting dynamic updates to very specific hosts. Turn off requests queries. This will stop cache corruption. Now, what I should mention here is, I'll tell you is how I do this, because I basically do all these functions, but I don't do it at the DNS server. I do it through router access lists, and there's some firewalls involved as well. But basically, the best way to do it is to have the access list deny any UDP queries to your server for, other than what's internal. What this does is it prevents other people from corrupting your cache. If they can't reach your server to run queries against you, then they can't corrupt your cache. Block any kind of UDP traffic over that way. Actually, the bottom line is you should turn off recursive queries if you can. If it's authoritative, you should separate out servers that are authoritative and servers that are recursive. In fact, one good way to do this is to have an internal DNS server on one side of a firewall and an external DNS server on the other side of the firewall. This is another way to help prevent cache corruption. There are also lots of application firewalls that will sit on the front of your DNS server and prevent any kind of real cache corruption. It does the same thing. There's tons of things. There's things you can do with your bind. If you're running bind, you can configure bind so that it will not accept non-authoritative answers. So when it sees an entry come through for www.foo.com attached with www.somethingelse.com, it will automatically reject it as it's non-authoritative. This can be a little bit problematic because if somebody has made a mistake in their zone file, all of a sudden it'll turn their server non-authoritative and it'll reject everything from there. But in my opinion, that's the other person's problem, not mine. So, and there's many things you can do within bind like that to make it more secure. Let's see. Okay, that's pretty much it. Does anybody have any questions?
Can we get a copy of the brief and provide your email address?
What's that?
Can we get a copy of the brief and provide you?
Yeah, in fact, the slides are different than what's in the book, and we're making copies of them, and they're going to be available for everybody, the new set of slides.
Now, you said that if you have a query and returns no such records, it also will return the previous and the next one, which you're going to query for one and stop
Right.
I was going to know the previous and the next record of one doesn't exist.
What it does is it's in the spec, and basically it parses the zone and creates a canonical list very specifically based on how the spec addresses to do it. So that's the first thing it does when DNS starts up. So then that's how it knows what's first and last.
Seeing as that's the case, and if we send both first and last, could you just try to program that will capture all addresses returned? Essentially, it's doing the zone transfer. You can get all the information.
Yeah, you could do something like that. If you, although one of the things that you'll find is, and I should mention this, there are ways to modify bind and also this new security ones that if you get too many fails, it'll start notifying you, and which is a really good thing to have. That's one thing that's really important in security in general. It's really important to have your things locked down, but it doesn't matter how tightly locked down you think things are. It doesn't matter how strong your encryption is. Somebody can break it. It's always a good idea to have a mindful eye, watchful eye on the logs, on the system, and make sure there's nothing going on. I remember a situation at a particular company where they had an FTP server that got turned into a where site, and it was 6 months before they figured out that it was a where site. And it basically ran out of drive space. Something that could have easily caught if somebody had been keeping an eye on the logs. And that applies with DNS. If you're seeing tons and tons of errors, failed domains, you know there's something going on, and you follow through with some of those things.
Use TCP routers to enhance your marketing.
Yeah, that's not a bad idea. Especially if you're using Unix. If you're using NT, it's a little bit more complicated to do that. But yeah, TCP wrappers, specifically for the auditing function, is very good that way. Any other questions?
Yeah.
Oh, yeah.
Fragmented UDP packets coming out of DNS servers. Like,
Yes.
do you have any insight into that? Or?
Fragmented UDP packets? Denial of service attacks. There's nothing it's going to be able to do to corrupt zones or actually even gain access to your server. It'll be purely a denial of service attack attempt. As far as I know, that doesn't even work anymore. Other than maybe it might fill up your line. But if you've got a decent enough pipe, it won't make any difference.
What log analysis tools do you use?
Log analysis tools that I use? Perl. Yeah, I can't remember, there's one I was trying on Linux, but I can't remember what it's called now. But usually I pretty much wrote all mine in Perl.
How do you feel about Microsoft version of DNS versus Vine?
How do I feel about it? Well, it depends on which one you're talking about. Because there's, the NT4 version, and there's this completely new Windows 2000 version, which, attaches itself to this dynamic or the directory structure, and which is a whole separate monster. Well, I mean, to be honest, security-wise, it's pretty comparable. Microsoft has been pretty good about when the cache corruption bugs come out or somebody finds another one, they pretty much jump right on them and they fix the DNS one. Speed, as far as the tests that I've run, the Microsoft one's a tad bit slower. But other than that, the Microsoft DNS does conform very well with the spec. A couple bugs here and there that they fixed, mostly with IPv6. But overall, I'd say it's pretty comparable.
Reasonable amount of security.
Yeah, I mean, I'm just the DNS aspect. I'm not really getting into the NT aspect, but just as far as DNS is concerned. Yeah. Right. A little bit louder?
You mentioned Wiz.
Right.
Dynamic updates. Are there weaknesses in the safety of DNS when it's done on Microsoft DNS? It's done with Wiz.
There are some weaknesses there, although, I mean, the weaknesses are going to be different, obviously, because you've got really two different types of systems. One is still very much DNS, another one is a NetBIOS thing, and Wins is susceptible to any NetBIOS type attack. I would say the little bit of ones I've found with problems is basically using Wins to corrupt your DNS. And that's kind of thing that more happens internally since nobody really uses Wins on the internet. But you can very easily corrupt the DNS infrastructure internally by flooding bad Wins entries, which then will try to query DNS. Anybody else? Okay, well, thank you very much.